So now we're going to talk about some important set operations. All right, so when you learn about numbers, you learn about different operations you can do with numbers, like addition and multiplication. So we're learning about some operations that we can do with sets. So first one, well, one of the important operations is union. So suppose A and B are sets. The union of A and B is the set, which is written like this: A union B, which is defined as follows. It's the set of all x such that x is an element of A or x is an element of B. So here's a diagram that helps us visualize this. So first, we write out the sets A and B. Now the set on the left is A, the set on the right is B. We write each one as a circle. Now we write them with some overlap because it's possible that there is in fact overlap among A and B. In other words, the set of students taking discrete math this semester is a set. And then there's another set, the set of students taking Calculus 1 this semester. But there is some overlap among the between those two sets, right? So in general, whenever you have two sets, it's quite possible that there is going to be overlap between them. So we draw them to account for that potential overlap. Now you might say, well, hold on, what about if there is no overlap? Is this diagram inaccurate? Well, in that case, well, no, the diagram is still accurate because that middle part could be empty, right? We're just drawing a place where the elements of A and B could be. Okay, the middle part might have elements in it, right? There might be some people taking discrete structures at the same time as they're taking Calculus 1, which is pretty common, I assume. Or maybe there are no people in that overlap. Maybe there is no overlap, but the point is there's the possibility of overlap, and we have to account for that. Now we want to indicate what is the union of A and B. So the union of A and B is anything that's in A or in B. So the shaded area, this entire shaded area, is the set A union B. Okay, so this diagram with just the shaded area, the shaded part of this diagram, which is the entire diagram, is A union B. Here's an example. If we have the set 1, 2, 3, and the set 1, 2, 4, and we want the union of these two sets, it is set 1, 2, 3, 4. All right, the set of all elements that are either in A or in B. And notice, if they're in both, it's not a problem, right? If for example, this number 1 is in the first set and in the second set, but no problem, it's still part of the union because it's an element of A or an element of B. That's true. The general meaning of or is inclusive. It could be that you're part of both. Okay, that doesn't invalidate you. Okay, that's one operation. Next operation is intersection. So again, suppose A and B are sets. The intersection of A and B is the set written like this: A intersected with B, which is defined as the set of all x such that x is an element of A and x is an element of B. So this is the set of all things that are in A and in B at the same time. So again, we have our sets A and B, and we want to indicate the intersection of A and B, which is this. So the intersection of A and B is exactly this part in the middle. All these things in this area here in the middle are part of A and are also part of B. So therefore, they are part of the intersection of A and B. So this shaded area is the intersection of A and B. Example, if we want the intersection of the sets 1, 2, 3 and 1, 2, 4, these two sets. So we want to look for all those elements that are in both of the sets at the same time. Okay, and there's only well, actually there are two candidates for that, and they are 1 and 2. So the set 1, 2 is equal to the intersection of these two sets. Next operation is difference, which is like similar to subtraction. So suppose A and B are sets. The difference of A and B is the set which we write as A minus B, which is defined as follows. It's a set of all x such that x is an element of A and x is not an element of B. So what this means is we start with things that are in A. If something is not in A, you can forget about it. It's not going to be part of the solution. So you start with things that are in A, and then you remove everything that's in B. Okay, so again, instead of all things that are in A, but not in B. So you start with things that are in A, but you remove everything that happens to be in B. So again, if we have our two sets A and B, and we want to indicate A minus B, we would do it like this, right? So this is so if we would just be talking about A, that would also include the middle part. However, we need to exclude everything that's part of B. So what we're left with is just the part in gray. Example. Oops. Right, so the set 1, 2, 3 minus the set 1, 2, 4. So we start with the things on the left in A, and we remove anything that is in B. So we have to remove the 1 and the 2. So what we're left with is the 3. Here's a longer example involving set operations. So let's say we have a set A, which is the set A comma B, and B, which is the set B comma C. Right, so it's a little confusing because uppercase and lowercase, but generally we use uppercase letters for sets and lowercase letters for elements. And then we have also set C. So if we want to find the following, A minus B, the difference of A and B, union the difference of B and A. Okay, so we'll do it in stages. So this is, well, we can write out the sets A and B. So this is right. And then we can do the stuff in parentheses first, as usual. The parentheses indicate do this first before doing what's outside. So now we have the set just containing A union the set just containing C, and then we get our answer, our final answer. Another example, again with the same sets A, B, and C. Again, we do what's in the parentheses first. Here we have the empty set because the intersection of the set A comma B and the set 1 comma 2, they have nothing in common. So the result of that operation is the empty set, and we want the empty set union the set A comma B, and the result is the set A comma B. The empty set in this case doesn't contribute anything because it has no elements. It's like 0 when you do addition, right? 0 plus anything is that thing, right? 0 plus x is x. So it's kind of what's happening here. Another example, again with A, B, and C. So here we're involving a Cartesian product, A cross B, the intersection of A cross B and B cross C. Okay, so we first have to find A cross C, and then we have to find B cross C, and then we have to find their intersection. Okay, so this is A cross C, and then B cross C, and we want to find their intersection. I just wrote it on two lines because there isn't enough room on this on one line. Okay, so is there an intersection among these? So notice the first set here on the first set that we're trying to find the intersection with. The first set has 4 elements, right? Each element is an ordered pair. So if A comma 1, A comma 2, B comma 1, B comma 2. And then the second set has also 4 elements, B comma 1, B comma 2, C comma 1, and C comma 2. These two sets have 2 elements in common, namely B comma 1, which is in this set, and also in this, right, which is here and also here. And as well, there is also the element B comma 2, the ordered pair B comma 2, which is in this first set and also in this second set. And those are the only 2 things they have in common, and therefore their intersection is the set of these 2 ordered pairs. Okay, now before doing the next example, we have to recall the notation for intervals of real numbers. Okay, so just look at this and make sure you understand it. Pause. necessary, as usual. So now we have an example of set operations. So true or false. This set, question is it equal to this set? Now, each of these is going to be a set of real numbers. The question is, are they equal? So, well, we can start with any of them and try to find the other one. In other words, what we'll do is we'll start with this. Start with this and try to see if we can figure out that is in fact equal to this other provided set. Okay, so this set is equal to the set of all x in the real numbers, such that x is between 0 and 3 inclusive. And then we have to do minus, so we have to find the set difference with the interval of real numbers from 1 through 2. So this is a set of all x in R such that x is between 1 and 2 inclusive. So now we have to think about what's the set difference here. So here we have all numbers, all real numbers, all real numbers between 0 and 3. But we have to exclude everything between 1 and 2. So we can go from 0 up to 1, but not including 1, because 1 already has to be excluded. And then similarly, we can go from 2 to 3, but not including 2. We cannot include 2 because 2 has to be excluded. So what we're left with is a set of all x in the real numbers such that x is greater than or equal to 0 and less than 1, or x is greater than 2 and less than or equal to 3. Okay. So we can write this like this. This is the set of all x in R, every real number such that x is greater than or equal to 0 and less than 1, union the set of all real numbers such that x is greater than 2 and less than or equal to 3. And which is exactly what we have here on the right-hand side. So we see that these two things are in fact equal. Here's how you can see it on a number line. Right? This is how this interval of real numbers, either one, again, we just determined that they're equal. So this diagram here is accurate for either one. So what you see here is it's the set of all real numbers starting from 0, going up to but not including 1, and then starting again from 2 but not including 2, starting right after 2 and going through 3. Now, before talking about the next set operation, we have to introduce the idea of the universe. So when dealing with a set S, we often regard it as a subset of some set, some other set, which we call the universe, or sometimes we call it the universal set. It's the universe for S. So again, we're dealing with a set S. S is part of a universe for that set S. So for example, when discussing the set of prime numbers, we might consider the universe of this set to be the natural numbers. That's a pretty natural thing to think about. When you think about prime numbers, as opposed to some larger set, you might typically think of natural numbers. Now, that's not the only set you might think of. So it usually has to be specified what the universe is. It's usually not so obvious, but sometimes it is obvious. But generally, it will be specified. So now that we have this idea of universe, we can define our next operation. Suppose A is a set with universe U. So A is a set, and it's part of this larger universe. The complement of A, which is denoted with A with this bar on top, is the complement of A, which is equal to the universe minus A, U minus A. So A is part of this larger universe. If you start with the universe and take away everything that's in A, you're left with the complement of A. In other words, the complement of A is everything that is not part of A, everything in the universe that is not part of A. Now, of course, when I say the universe, I don't mean what we normally think of as the universe, right? It doesn't include Napoleon Bonaparte, right? Even though he's part of the universe. What I mean is the universe for this particular set. So it's everything in the universe for this particular set, except for the elements of the set. So here's how we draw a set A, right? So this circle is the set A, and we write the name, we write the label, we write the name of the set outside of the set. At least that's my style. So so the square box is not A. A is the circle, and the square box is the universe, U. Okay, so A is part of a universe. If we want to write the complement of A, if we want to draw the complement of A, we would indicate it like this, right? We would shade in everything that is part of the universe that's not part of A. So it's everything in the universe except for A. That's a complement. That's the complement of A. So for example, let's say we have a set A, which is 0, 1, 0, 2, 4, and the universe is the integer is 0 through 5. Then the complement of A is the universe minus A, which is the set of integers from 0 through 5 minus the set 0, 1, 0, 2, 4. And what we're left with is the set 1, 3, 5.